cryptography is what we've been looking at recently, right? And it's this idea of taking a message, right? And we're going to put some more names on this, right? Taking some kind of text, right? And then you go through this process of encryption, right? Encryption. You might use something like a cipher. And what were the kinds of ciphers we've looked at over the past week or so? Was the very first one that we learned was the Caesar cipher, right? Not to be confused with the Caesar salad. And it's got some really big weaknesses, right? And so there are lots of ways to overcome that. The next kind of method of encryption we looked at was it needed a physical thing. Do you remember? The one-time pad. Excellent, Kavas. Okay? You've got these different processes. That's what you do. And what you end up with, and this is a new word for you, is because it's text that's gone through a cipher, we call it ciphertext. Okay? So you have your original message, it's encrypted, and then this is what you end up with. Okay? Now, the reason why this, right, and particularly the process of encryption, is a mathematician's game, okay, is because text can be expressed numerically, right? So this data here, A's, B's, C's, D's, and so on, okay, if you can turn it into numbers, then this process of encryption can just be some kind of mathematical function. Any mathematical function, right? And it will lead you to an encrypted message. But it'll be more numerical data because numbers into functions still gives you numbers. Okay. So, therefore, this is why this comes under maths, and it's mathematicians who understand and work all of this stuff. Okay. Now, how are we connecting it to this? We looked at this idea under one of our earlier topics, right? Beauty in mathematics. And I told you there were all different kinds of symmetry, not just, reflectional symmetry or rotational symmetry. There were lots and lots of different kinds. And here is where we're going to look at another kind, right? So you've got encryption going in this direction, right? What is the opposite process called? It's called decryption. Very good, right? I mean, it's not that complicated based on the name. But think about this. Consider this, right? Encryption this way, decryption that way. If we are thinking about this mathematically, right? If a function goes in this direction, then what is it that goes in the opposite direction and takes you back? And we looked at this under the topic of matrices, right? That if you go in one direction and you want to reverse it, right? It's very similar to the word reverse, right? It's the word inverse. Good. So if you go in one direction with a function, you can go in the opposite direction with its inverse function. Okay? So this is really, really simple, an idea, but let's just draw up a quick table so you can see how this is going to work. Okay? So for instance, if the way you're doing your encryption, okay? Simple thing, okay? With our Caesar cipher, right? We used addition to all of those numbers, right? So 1 would turn to a 4, or 2 would turn to 5, and so on, okay? So if that's the mathematical function that gives you encryption, then the mathematical function that will give you decryption, that will reverse that process, is the inverse of addition, which of course is subtraction. So that's simple, right? Well, suppose instead of that as our encryption function, right? Suppose we use multiplication. I know mathematically it's kind of trivial, but suppose you took every number and then you multiplied it by 3, for instance, okay? If multiplication is your encryption, then your decryption function will be its inverse, namely, good, division. Okay. Now, there are more of these, right? For instance, I was showing you this under inverse notation, right? If you, I don't know why you would, but suppose you used like a trig function to do your encryption, right? If you did say sine of whatever the number was, like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, etc., right? Well then in order to decrypt, to go from this and to come back, you would use its inverse, which very unimaginatively is named sine inverse, right? Or inverse sine. So you do this. Okay? But we can keep going. Anytime you can think of a function, right? For example, if it was not just multiplication, right? But if it was multiplying by a matrix, right? What would you do to get the original message back? Because there is no matrix division, right? But we learned there are inverse matrices, right? So you would work out what the inverse matrix is, and then you multiply by that, and that should return you to your original message. Okay. So this idea here, can you see that this kind of way of approaching encryption is symmetrical? Okay. If you know what this is, you'll know what the other side is. They are exactly like they're two sides of the same coin. Okay. So this whole idea, everything here, right? This is called symmetric cryptography. That's a bit messy. Okay, to give you a bit of a picture, right? And I would love you to draw this picture as well. If you had two people, right? Person A and person B. Okay. The idea is that each person has kind of like a key, right? So this is what a key looks like, right? They've got a key and they use that key to lock up their message, right? They put it in a box and then they give it to B, okay? Now B, to unlock the message, needs to have exactly the same key, right? So here's the key, right? They use that key. So if I know that you're going to add 5 to everything, right? That's the same as knowing I need to subtract 5 in order to get back the original message. It's really the same key, right? And for that reason, I can send messages back and forth using the same key, okay? And that key might be one of these things, or it might be like a one-time pad, right? Whatever it is, you have to have it on both ends. Hence the name symmetric cryptography, okay? But when we were looking at one-time pads, we saw that this is not perfect. There are big problems here, right? Not least of which is the fact that you've got to get the same key to each person, right? And if you are separated, how do you do that? Do you mail it to them? Well, someone can get the key, right? So this is a problem. And what if you're on the internet? What if you want to send stuff securely? How do you get the same key in both people's hands, right? The short answer is you cannot. Okay? There is no way really of securely trading keys, okay? So therefore, this system, as effective as it is, can't be used for most modern cryptography, okay?